Who knows what a neutron star is? Who knows where they start, where they come from, where they go? Who knows about the fundamental physics that underpin everything that we do around us? I don't, for sure, I don't know all of that. But there are people that start to have ideas. Well, tonight's guest and speaker, Andreas Schmidt, is going to talk about using those fundamental laws and the mathematics and the physics that underpin them to understand what happens in those neutron stars, to demystify them and inform us about what we experience in the world around us now, and use that knowledge from the neutron stars to explain what we look at in front of us today. So I'm not going to spend any further time talking about that, because that's what he's here for. So what I'd like you to do is give a large round of applause to welcome him, and appreciate the effort that he's come to come here and speak to us tonight. Mr. Andreas Schmidt.
Thank you very much. Does that work? Yeah. Okay. Thank you very much for this very nice invitation and for the introduction. I'm very happy to see so many people here. So many people interested in science, especially in fundamental science. Usually when I give talks at workshops or conferences, the audiences are smaller. So thanks for coming. What I want to do in this talk, basically I want to tell you what connects these two pictures. Right, so this is an astrophysical picture here. That's a picture of a neutron star, and I will explain what a neutron star is. I know that not everybody, or maybe nobody, knows what a neutron star is, as Nick just asked. So this is obviously an artist's picture. That's not a real picture that we can take. So you see this sphere, that's the neutron star. There's some magnetic field lines. There's some stars around it. And on the other hand, that's a nucleon. That's either a neutron or a proton, pick whatever you want. And you see some substructure of this neutron or proton. So I'm kind of assuming that most of you have heard what a neutron and a proton is. Is that right? Okay. Maybe fewer people of you know what a quark is. I'm not assuming that, but maybe you've heard about quarks, maybe not. So these guys you see here are called quarks. So these are the constituents of a neutron or proton. So there are three quarks that make a neutron or proton, and they are depicted here in three different colors. That's not accidental. Actually, they carry something that physicists call a color charge. It's not real color, but it's a name that we give these charges. That's why red, green, and blue is not a coincidence, but that's nothing to worry about now. Anyway, I want to tell you why these two pictures are connected, and this is surprising at first sight, because this is a macroscopic object. I put here the scale. Actually, for a star, it's surprisingly small. We'll come back to that. Just wanted to remove that cursor to some corner. So for a star, it's surprisingly small. We'll come back to that, but nevertheless, it's a macroscopic object. So this diameter or radius is of the order of 10 kilometers, whereas this guy here has a radius of the order of 1 femtometer. Right? And for femto, you have to go all the way down to 10 to the minus 15 meters. I guess most of you have seen this notation, 10 to the minus 15, which means it's a 0 followed by 15. Or at the 15th digit, there's a 1. So I wrote it out here just to make it even more striking that there's many order of magnitudes difference between this object and this. And nevertheless, I want to explain to you in this evening why we need to understand the physics of this object to understand observables from the star. Okay, that's what I want to try to explain. In other words, why are neutron stars laboratories for fundamental physics, right? So this is governed by the fundamental laws of physics on the smallest scales, and I will claim in this talk that this is one of our laboratories, or maybe the only one even, where we can learn something about this fundamental physics. Okay, but I want to start with a little journey. Let's forget about neutron stars for a second. I'm like taking the view of some people here. I should maybe walk around a bit. So let's start with a little journey, and the journey starts with a very simple question that every child could ask: what happens to matter if you squeeze it more and more? Okay, take any matter and imagine you have all power in the world or all force in the world, and you squeeze it. Right? So that's at first sight it does sound very exciting, because the first thing that will happen, everybody can imagine. Let's look at this first step here. Suppose you have some gas, like air, in this container, and you have a piston, and you apply some pressure on it. You compress it, right? Not very exciting. And this is visualized here. You push the piston, you get a denser gas. If you release the pressure, you get a less dense gas. And this is shown here by these little dots, which are supposed to symbolize the molecules. So the average distance of the molecules here is larger than here. That's what we mean by density. Right? So fewer particles, molecules, and so on per volume. That's what density is. And obviously this is a higher one. You can also think of it of mass per volume. This has a higher mass per volume than this, so this has a higher density. But nothing very, very exciting has happened. Notice, of course, that this in air, the molecules are not ordered as they are shown here. They're just moving around. So that's why I said the average distance of these is larger here than here. So that's the first thing. Take any material and compress it a bit. But what I want to do is I want to go further. So let's keep squeezing. So now let's say again, these are the molecules of my gas. They have a certain average distance. But let's now squeeze until they start to overlap. Okay, now I have really the molecules, the inner structure now becomes important of these molecules. They start to overlap, and what I mean by that is, if we zoom in on a microscopic level, then these little balls here really aren't balls, but they are atoms which have a nucleus and electrons going around. I'm sure most of you have seen these kind of pictures. If not, let me just explain what this means. That's the nucleus of every atom. Has a nucleus depending and containing neutrons and protons, right? Let's say the protons are black, the neutrons are pink for no particular reason. I just wanted to distinguish them. So we've got neutrons and protons in the nucleus, and we've got electrons going around them. Here depicted as orbits. If you've heard of quantum mechanics, you know that's not quite true. It's rather clouds. Electron clouds going around, but this doesn't matter much. Let's think of this going around in orbits. And what I mean by overlapping atoms or overlapping molecules is that now this electron, well, it kind of stops knowing whether it belongs to this one or to this one, right? They overlap, these clouds, and you get some different kind of matter. That's where it gets interesting. And what I want to do is I want to keep squeezing. So if we keep going, so this is our overlapping atom picture. So we've got electrons, neutrons, and protons. And suppose I keep squeezing until even the nuclei overlap, right? So all of a sudden, if I'm a neutron here, I don't know anymore, do I belong to this nucleus or to this? So it's rather a soup of neutrons and protons and electrons. Rather than the structured objects here. Notice that I could have started from any material, because I lose the material properties. Right? So whether I start from, I don't know, a metal or a gas or wood or whatever, that's encoded in that structure. But if I squeeze so much, all this structure is lost. You could start with anything you want. If you get to that level, it doesn't matter what you've started with. Okay? So this is what I will refer to nuclear matter. It's just this soup of neutrons and protons and also electrons, which for simplicity I haven't shown here. Now let's keep squeezing. Can I go to the next level? Can I squeeze these neutrons and protons such that even they now overlap? And that's where I get to the next level of next microscopic layer. As I briefly mentioned at the very beginning, each of these objects in turn is composed of 3 quarks. Right? So if you've never heard of quarks, this is a little picture of them. As I said, they come in 3 colors. quote unquote. That's a name for a certain charge, which is not that important, but that's the reason I depict them in red, green, blue. They also have something called flavor. That's maybe for the expert. I will never use this again in this talk. And this flavor is called up and down in this case. But never mind. Each of these guys is composed of 3 quarks. And you can also see that that's what makes the difference between a neutron and a proton. It's different flavors of quarks that distinguish between them. Right, so here we are learning some particle physics. Depending on which quarks form such a nucleon, it's either a neutron or a proton. But it doesn't matter much now. What matters is, if we squeeze even more, that now even a quark in a nucleon doesn't know, do I belong to this one or this one? If they overlap, I end up with this soup of quarks. Okay? And there are also still the electrons, which I've dropped for simplicity, and something called gluons, which provide the interaction between the quarks. Again, for simplicity, I'm dropping this. So by squeezing more and more, we've arrived at this soup of quarks. So obviously we can do this in our head, but what have we done now by thinking of this compression, this squeezing process? So let's estimate the density that we've created, right? We've created denser and denser matter by squeezing more and more. So here's a little calculation, one of the 2 or 3 formulas I have. So the density, the mass density, is the mass over the volume. To estimate the density of this soup of neutrons and protons, this nuclear matter, let's suppose they are just space filling, right? So they just start to overlap. Okay? Then the density of this whole system is simply the mass of a nucleon divided by the volume it occupies. Right? That's the average density of the whole system if they just touch each other. Okay? So let's do this little calculation. So the nuclear mass, of course, given in units of everyday life, it's incredibly small. But the point is, also the volume is incredibly small. Right? So here's this femtometer I had at the beginning. So that's roughly a femtometer that they occupy. And the volume is a length cubed. So that's how we get density. And if you work out the numbers here, what you get is this. And this might not mean much to you. Let's say it's a very large number. So centimeter cubed is just a sugar cube size. Right? Centimeter cubed is a little sugar cube. And obviously it sounds very large. Right? 10 to the 15 grams. Of course, notice it doesn't matter much whether it's kilograms or grams. If it's kilograms, then it's 10 to the 12. Still very large. Right? So it's a huge number. But how huge? It doesn't mean much to me either. To get a comparison, what I did here is I calculated the mass of all human beings together. So just yesterday I googled the world population, about 7.7 billion. And let's say an average weight of 70 kilograms. And what you get is roughly 5 times 10 to the 14 grams, all human beings together. Right? So what we got here is roughly the same, a slightly larger number than the mass of all human beings, compressed into the size of the sugar cube. Right? So that's what this is supposed to symbolize here. So the sugar cube we've created by our little picture of squeezing more and more is incredibly dense. It contains all the mass of the whole world population. Okay? We could do this in our head, but was that completely crazy? Is that just some game we are playing here? So of course the next question is, where is that does that matter exist anywhere? Okay? Or is it just a game we are playing here? So let me answer this question by doing another little estimate here. Let's now go away from this sugar cube size, and let's take this matter, but now distribute it over a sphere of 10 kilometers. Okay? So I keep working with this, what I call nuclear matter, but now instead of looking only at the sugar cube size, I create a ball of radius 10 kilometers with the same density. Okay? So what I calculate here is the mass of this 10 kilometer sized ball. And obviously I'm doing this by multiplying the density with the volume of this ball, right? So the radius is 10 kilometers, volume is radius cubed times some factors which I don't care about. That's an estimate only, right? So there's a 4 pi over 3, which doesn't matter much, times the density we've just calculated. Okay, and again, you can work out all these numbers, do this little multiplication, and what you get is 10 to the 30 kilograms. Again, very large number, doesn't mean much to me. What does it mean? And then when you look up the mass of the sun, you find that's roughly the mass of the sun. Okay, so this incredibly dense matter distributed over a sphere of radius, or ball I should say, of radius 10 kilometers, has the mass of the sun. And that's another way of saying how incredibly dense that is, because the sun has 1.4 kilometers radius. Right? So what we have done, in other words, we've taken the sun, the huge sun, and compressed the matter to a ball of size 10 kilometers. Okay? So that's another way of thinking of this incredibly dense matter. And one way to understand this, of course, is that you might think, how can we ever create this dense matter? The point is, of course, it just tells us how much empty space there is in us, in everything, in the atoms, right? What we've done, basically, we've gotten rid of all this empty space and only took the density of these nuclei and put them together, and this gives us this huge density. Right? So that's the way to understand this. Get rid of the empty space between the nuclei and you end up with this incredibly dense matter. Another way of saying this is, of course, if you have a large nucleus, that's the density inside that nucleus, basically. Okay, but now we are basically there because that's exactly a neutron star. A neutron star, we know from astrophysical observations that it has roughly 10 kilometers radius and roughly has the mass of the sun. Right? We know there are many things we don't know about a neutron star, but that's a rough estimate we can be sure about. So we know the density must be incredibly large and roughly of the size that I just obtained by my journey of compressing any material. Okay? So this was not just a game. This kind of matter exists in nature in a neutron star. Of course, what I've done in my head was easy. When you want to do this in practice, you need an incredible amount of energy. You can't just do this in any lab. I later tell you that on Earth we can do something similar. We don't quite get to these densities, but there are some experiments on Earth where people try to create this matter, but it's obviously very difficult. You need a huge amount of energy. But in an astrophysical setting, what gives us the force that compresses matter is gravity. Right? You put this matter in a small region, and gravity then is strong enough to compress this to this incredibly dense matter, or nuclear matter, as I call it. I said that the neutron star mass we know is roughly one solar mass. There are neutron stars measured to have about 2 solar masses. That's the range we can infer from observations. So let me explain this a bit more, what this means and why this is also interesting for fundamental physics. First of all, let me briefly explain this picture here. I won't say much about the astrophysical life of a star. I'm also not an astrophysicist myself, but at least to say this one thing, that a neutron star is born in a supernova explosion when an ordinary star can no longer provide the force to resist gravity. Right? The star collapses, it implodes, and then in a huge explosion throws out stuff. That's the stuff you see here. And the neutron star remains. Depends on the history of the star, whether the neutron star or black hole remains. Let's not go into these astrophysical things right now. Let's just to explain the picture to you. So that's a supernova remnant, and there's a neutron star. It's this little dot here. And as we just explained, there should be some kind of matter of this ultra dense stuff that I created in our little journey. I should probably say, you might ask yourself, why is it called a neutron star? I talked about neutrons and protons, and this picture shows that it's mostly neutrons. Let's say the pink ones are the neutrons and the black ones are the protons. It's not completely trivial to explain why there are many more neutrons than protons. It's got to do with some microscopic processes, how neutrons and protons are converted into each other. And if you do the calculation, then you see that there's some balance in this process if there are roughly 90% neutrons and 10% protons. Right? Just to explain to you why it's called a neutron star, not a proton star. So it's neutrons and protons, but mostly neutrons. But here I've listed also there are already some questions that are unanswered, unknown in current research even. I told you that if you squeeze enough, if the densities are large enough, you get to this new phase where you rather have a quark soup than a nuclear matter soup. Now here's a theoretical question, we don't know, at which density is this transition? That's one fundamental question. When does it become theoretically better to describe the stuff in terms of quarks rather than nucleons? We don't know. It may very well be that you reach this inside a star, but that's an open question. So is there quark matter in neutron stars? Is a question that, for example, I work in my research. Let me also tell you that this is often called strange quark matter. This goes back to the flavors I mentioned at the beginning, the up and down. So if you know a bit of particle physics, you know that there are 6 flavors in general. It's up, down, strange, charm, bottom, top. Here we are only interested in 3 of them. But since the strange quark, these are just names obviously, just funny names. Since the strange quark plays a role, it's for that reason called strange matter. And stars that entirely consist of this, that's an hypothesis, it's possible, we can't exclude this, but that's another question we want to answer. Are there pure quark stars? Stars made entirely out of that matter rather than that matter, they are called strange stars. Let me put this into some context. So if you have heard of particle physics, obviously this is also sometimes in the news. Think of experiments at CERN, for example, the Large Hadron Collider, where they smash particles onto each other, where they discover new particles. The Higgs boson, probably you've heard about this. There are many other particles in the middle of the last century. These particles were discovered step by step. So usual particle physics is about properties of single particles, right? So we've discovered the Higgs boson. We want to know its mass, its other properties, how does it decay, in which time does it decay, and so on. What this problem poses to us, the question this problem poses to us, is different. Here there are many particles. It's what we call a many-body system. So it's a complex system which is governed by the fundamental interactions, namely the interaction between these quarks. And that's quite unusual, right? So complex systems exist, obviously, in nature. In material science, you're interested in the structure of metals, of compounds, right? So this is a complex system of many particles. How do they arrange each other? In which lattice structure do they sit? And so on. And here we've got a system where we can ask the same questions, but they are governed by the fundamental interactions rather than electromagnetic interactions, which are important for usual materials. Okay? So that's why this is so interesting but also challenging. We have a complex system governed by nuclear forces, by the fundamental interactions. And we can also ask, I asked this question already, can we create this on Earth? Are there experiments? Obviously that's very difficult, but there's an experiment which comes relatively close. So I'm sure I've already mentioned this a minute ago. Most of you have probably heard about the Large Hadron Collider in CERN, right? So it's a huge underground collider where particles are accelerated and then smashed onto each other to produce stuff, right? And we want to learn about the interior of these particles and the properties of these particles. And there's one experiment which doesn't smash protons onto protons, but which smashes real nuclei onto each other. And by doing this, you create matter rather than just single particles. right? So this is shown here. You take a nucleus, shown by these white balls. Now the white balls are the ones that were pink and black in my previous slides, the neutrons and the protons. So they hit each other, they collide, and while they are doing this, and then go on in the accelerator, they have created this soup of quark matter. So that's exactly with the same colors that I depicted before, and this is usually called the quark-gluon plasma. So this, at least in the way I'm showing it here on the slides, looks quite similar to the stuff I was talking about before, right? There are differences. It's still difficult in this experiment to create the large densities, and also usually this one is hotter than matter inside a neutron star. One difference is, for example, that this quark-gluon plasma contains antiquarks as well. Some of you might have heard of antimatter. That's what we create by this, by converting the kinetic energy of the nuclei into quarks and antiquarks. That's not what we have in neutron stars. In neutron stars, we have just, let's say, ordinary matter. Okay, so that's what's inside a neutron star, and that's why it's a bit difficult to conclude or to infer properties of that neutron star matter from this experiment. But there are new experiments being planned and being set up as we speak. For example, in Germany and also in Russia, there's one which are dedicated to produce matter closer to neutron star matter. So this is going to be very interesting in the near future, or in the next, say, 10 years or something. All right, so to further explain these complex systems and the questions we have in current research, let me make the comparison to the phase diagram of water. Right? So this is something probably everybody can relate to. You might not have seen this phase diagram, but you know that at atmospheric pressure, if you increase the temperature, you start from ice at very cold temperatures, then you've got water, liquid, and then you've got water vapor at some point, right? And this whole thing that collects these phases is called a phase diagram, and these lines are called phase transitions. Okay, I go from ice to water to vapor. There can be interesting things like critical points where I can go around in a smooth way. So that's what a phase diagram does. And I've just told you that we are now interested in a many-body system, or a complex system governed by the nuclear force. So you can ask the question: how does the phase diagram of this fundamental interaction look like? Right? And I haven't said this, but the fundamental interaction that governs all these interactions of the quarks is called quantum chromodynamics. Here you see chromo meaning color. That refers to the color charges, red, green, blue, that I showed in the picture, right? So from a theoretical point of view, we know that theory. Actually, we can write down the theory in one line, basically. I resisted the temptation to show this formula here, but I could write down the theory basically in one line, but solving it is incredibly hard, right? So just putting this theory or applying it to a many-body system which has a certain temperature and a certain density makes it incredibly difficult. So basically, from a theoretical point of view, you would like to understand this phase diagram, but we know very little about it. Okay, and to put it into the context of what I said before, neutron stars sit here. So on the scale of these fundamental interactions, they are relatively cold, actually, even though their temperature is 10 to the 10 Kelvin or something. So for daily life standards, it's incredibly hot. But since we're dealing with huge energy scales when we talk about fundamental particles, on that scale it's actually cold. So it's colder than the stuff we create in this hadron collider that I just mentioned. So the squeezing thought experiment that I did at the beginning basically took us from here, a small density, up to here. And that we expect that there's some kind of phase transition like this from the nuclear matter to the quark matter that I showed in these different pictures, right? This is called hadronic matter in a more general term, The confluent plasma sits here, and we would like to understand how where this phase, this line is. Notice I've not put any numbers here. Here in water, obviously we know where these phase transitions happen. Here I was very schematic, and the main reason is we don't know. I could have put some more details, we know a bit more, but roughly speaking, many details are just completely unknown. It's just too hard to solve this theory. And that's also why I said in the beginning, the talk is about how to, not only from the astrophysical point of view to understand what's inside the Newton star, but also to use the Newton star to gain information about the fundamental theorems. Okay? All right, so in the final 15 minutes or so, I just want to flesh out a few properties of Newton stars and how we look inside the Newton star, in quotation marks, how we use observations and connect them to observables. So what I'm going to start with is the mass of a star. So there are certain Newton stars, not all of them, of which we know the masses. Don't ask me in detail how this is measured. As I said, I'm not an observer or astrophysicist, but I know that what you make use of is that some of the Newton stars are in binary systems. So there's a Newton star and some other star, which can be a Newton star as well, or can be some other stuff like a so-called white dwarf or something like this, and they orbit each other. Okay, similar to the Earth orbiting the Sun. And these systems, in these systems, you can somehow infer the mass of the Newton star, and these are the mass measurements. So each of these numbers, which you can't read, is a certain star. The number gives the location in the sky. And this axis here is the mass, right? So this star, for example, has a mass of roughly 1.4 solar masses. So that's a unit of the solar mass. I told you already, somewhere between 1 and 2, right? So they're roughly between 1 and 2. They have different colors here because these are different classes of stars. I don't even exactly know what this means. We can ignore this for now. And notice also that some of them are not just dots, but have error bars. So we don't quite know where within this error bar the mass really lies. But the point I want to make here is that the fundamental interactions, which is governed by this quantum chromodynamics, QCD, leads to a certain mass of a star. So suppose you could solve this, then I could make a prediction for how heavy stars can be. Okay? So the logic is roughly like this. Suppose this is a very repulsive interaction, right? So it's very hard to compress this. So then we could say this is stiff matter. And then it turns out, if you add gravity to it, you can build very heavy stars. Right? So the idea that's behind this is always that the microscopic interactions, like the repulsion between the particles, gives an outward force, and gravity pushes inwards. And at some point there's a balance, and this determines how heavy my star can be. Okay? And the other way around, if the repulsion is very weak, then this is kind of soft, and usually the stars that we get from this are not as heavy. So I'm showing this in this little plot here with many colorful lines. So what this means is, as I told you, the fundamental theory is so hard we can't really solve it. What people do in research is they assume a model for nuclear matter or quark matter, a model for these interactions, and then they compute the mass of the stars they can produce out of that. And each line is the prediction for one model, right? So suppose I have my favorite model, and I compute all possible stars I can build with this, all possible neutron stars. Then they have, for example, this mass and this radius, or this mass and this radius, right? So I always get a curve. And as you can see, we know very little because there are many models, and they differ vastly from each other. But the logic goes as follows. Now take a measurement of a mass, and I've put in, there are 3 mass measurements here. So these are these bars here. As you can tell from the width of the bars, we don't know anything about the radius of this object. Right? We know radii of some other neutron stars, but when you can measure the mass, usually you can't measure the radius at the same time. That's a pity, but that's what it is. So we have these very wide bars, but quite narrow in this direction because we can measure the mass. Suppose my favorite model is this one. And then I measure a neutron star with this mass, which means this model is excluded. Right? Because all these curves, even though it looks very complicated, have a very interesting property. They have a maximum mass they can reach. None of them goes to arbitrarily large masses. Right? So that's what we do in the research connecting fundamental physics to astrophysics observables. We compute the mass and the radius, for example, from a given microscopic model, and then see if it's excluded or maybe confirmed by observations. And of course, as you can see, as I said, it would be beautiful if we had also a simultaneous radius measurement of them. Right? This would make our life much easier. And indeed, there's a relatively new experiment taking data right now. It's on the International Space Station, some detector that receives X-ray signals from neutron stars. And this helps us to determine radii of the stars. And so there's some hope that this gets better and we can constrain our microscopic physics even more. All right. This is just to explain you that, I mean, you've probably already learned from what I've told you that the physics that goes into neutron stars is quite rich. Right, and here are the 4 fundamental forces, and they are all relevant. So that's why it's a lot of fun to work on neutron star physics, but it's also quite challenging. So if you don't know this, I'm sure most of you or many of you have heard about the fundamental forces. Everybody knows gravity, right? That's why we are pulled down by the Earth, and everybody knows electromagnetism. These are the forces that we experience in daily life, more or less. What is more exotic are the forces I already talked about, and they are usually called the weak and strong nuclear forces. The strong interaction is exactly the QCD that I talked about before, the quantum chromodynamics dynamics. Weak interaction is responsible for some nuclear decays. But these forces together, in principle, explain everything. Right? There's some open questions which cannot be explained, but that's the so-called standard model, and it's very well confirmed. So everything that we see and measure, with some exceptions, can be explained by these interactions. And the interesting thing is that they are all, in some way or another, important for neutron star physics. I put some examples why they are relevant. I already explained, and it's quite obvious that gravitation is relevant to keep the star stable. Otherwise, there wouldn't be a star to begin with. Strong interaction, I have explained, right? It gives us the repulsive microscopic forces, stability of the star. So mass and radius would be influenced by this. I haven't talked about the weak interaction at all. I don't want to say much about it. But for example, we can observe also temperature of a neutron star and the temperature change over time. And we know it cools, and we believe that it's due to some neutrino processes. So let's not go into these details. And electromagnetism is also important. Remember the first picture I showed you. Neutron stars have large magnetic fields, for example, so we also need the electromagnetic forces or interaction. Here's just some, to give you some more idea about open questions in current research. That's a bit of a more detailed picture of a star. Let's maybe first go to this little sketch here, and let's look at this neutron star here. When I talked about the density of the star, I neglected the fact that actually we have a density profile. We go from relatively low densities at the surface to larger and larger densities in the core. So the really exotic stuff I was talking about happens here in the core. That's where there's basically a huge question mark. We don't quite know how to describe this and what this is. We have a much better idea about these outer layers, and interestingly, there's something called a crust. So this is almost like a lattice structure in a metal or in a usual material, of course under extreme circumstances, but it's very similar. That's why we call it a crust. This is also interesting for some observables we have. This is more standard nuclear physics, so to speak, rather than the exotic fundamental physics of quarks and gluons. To give you just some facts about neutron stars to show that they are quite extreme, not only in their density, they also have huge magnetic fields. As a comparison, 10 to the 15 Gauss might not mean much to you. So the Earth's magnetic field in these units, Gauss, is about 1 Gauss roughly, right? So this is 15 orders of magnitude larger. You have an ordinary handheld magnet, it's about 100 Gauss. So that we can't produce these kind of magnetic fields in the lab. So this is huge. They rotate extremely fast. I told you that they are, for a star, they are quite small, but of course they are still macroscopic objects, right, of the size of 10 kilometers. And now I'm telling you, they rotate about, the fastest rotators rotate 700 times per second, and that's, of course, a lot for such a microscopic object, right? I once did a little estimate, it's very easy to do. With this rotation speed, a point on the equator moves with, I think, 20% of the speed of light. So this is really fast for such a macroscopic object. I told you that we are talking about many body systems, complex systems in this star, and this is not unlike usual material science in some way. And indeed, we have effects like superconductivity and superfluidity of this matter, of the nuclear matter or the quark matter. Actually, this is where a large part of my research sits. I'm interested in superconducting, superfluid properties of this matter. And indeed, here we also want to connect this to astrophysical observables, to look inside the star and really say, is there a superfluid, is there a superconductor? From a theoretical point of view, we do expect this. Right, so this is part of ongoing research. Finally, not sure how many, I don't want to go over time, so maybe 2 or 3 minutes, just let me mention that on top of some of the observables I just mentioned, there's a new one since 2 or 3 years, namely gravitational waves. So this was certainly also in the news for the first time about almost 5 years ago, 4.5 years ago or something like this. So what gravitational waves are is depicted here. So you've got a system of 2 neutron stars, for example, right? I told you they are binary systems of 2 neutron stars, which orbit each other. Over time, they lose some of their energy, their rotational energy, because they move closer together. And this energy is emitted in the form of gravitational waves. Right? Gravitational waves are quite interesting. It's quite an interesting phenomenon. Think of water waves where water molecules oscillate, or maybe you've heard of electromagnetic, well, I'm sure you've heard of electromagnetic waves, where electric and magnetic fields oscillate. In the case of gravitational wave, it's space-time itself that oscillates, which is very hard to imagine. But that's what this picture is supposed to illustrate, right? So this is space-time, which oscillates. And this we can measure now. That's quite an achievement. A lot of technology went into this. This is the detector. I don't want to say too much about it. But after a long time of refining the experimental methods, developing a lot of new technology, people were able to detect the gravitational wave from a neutron star merger. First, it was done for a black hole merger. You can have 2 black holes doing the same thing, basically. It's easier to detect. It's stronger gravitational waves. But there's one event so far. There's some in discussion and some possibly observed in the past months. But one that is solidly observed of 2 neutron stars. Okay? And that's another source of information we have for looking inside the star. That's still at the beginning, of course, it's only one event. Here's the event, by the way. So this is the signal. It's very hard to see, especially when you're at the back of the room. So maybe here is the best to see. There's a little light curve here. And this is the frequency versus time. So what you basically see, or what you hear, is something like... That's what it means, right? I go to higher frequencies. Think of a little bit like when you spin a coin on the table, right? It goes like... Okay? And that's what it is in the last stages of this merger process, where the neutron stars orbit each other, and then they merge to one object, right? That's what you see here. And there are 3 detectors. 2 in the US, 1 in Italy. That's why there are 3 plots here. And what people are now trying to do is to relate simulations where you need a microscopic input for the nuclear matter, the quark matter inside the star, relate this to the signal, and maybe distinguish between different kinds of matter inside the star, different kinds of microscopic properties. This is a picture of a theoretical simulation that is done for such a merger process. Huge computer power is behind such a simulation. I've not done this, I've just stolen this picture. So here you see, for example, I think it's temperature on one side. They can track the temperature at every point of this merger process and density. But the logic is very similar to the mass radius example I showed you before. You make an assumption for the microscopic composition of the matter, you run the simulation, and then you check whether it's in agreement with what we observe from the gravitational wave detector. If it's not, then you have to use another model. Right? So that's how it works. And that's why this research field is quite exciting at the moment, because this is all very new. Okay, sorry for taking a few more minutes than planned. So instead of a summary, I just want to put up this. Neutron stars are fascinating objects and the physics is extremely rich. Whenever a physicist says the physics is extremely rich, it means we basically don't know much. So that's why this is certainly a work in progress. So thank you very much for your attention.
So thank you, Andreas. We're going to take a break now, and please help yourself to tea and coffee and cake at the
Okay, so who has the first question? Okay, lady back there with a
Furthest
whip
away.
in here. Okay, furthest away in
Work
it.
off this cake.
He needs the exercise, believe me.
What is the biggest neutron star you can have and why?
In radius or in mass?
You tell us.
In mass, we don't know. So that's a very interesting question, because that's something people have measured very recently. So I talked about this plot here, and these measurements I put in here are the heaviest measurements we have up to date. And they are quite recent. So a few years ago, this 2 solar mass star was measured. And yeah, you can ask now, how high can we go? Right? You see that there are some excluded regions. So things go wrong, become unphysical, or don't work. In this region, you collapse to a black hole, for example, or something like this. But if you are out here, well, that's basically an open end, right? So we would be very surprised if we find stars that are heavier than 3 solar masses, right? So we are probably somewhere in between 2 and 3 for neutron stars. If you're asking about the radius, my answer would be even more vague, because there the measurements are much worse. And again, since I'm not an astrophysicist, I'm not even sure what the range exactly is that people think the radius is. I told you it's roughly 10, right? So that's a benchmark. But whether it's 11 or 9 or 15, we don't really know. And it of course depends also. There might be stars with 14 kilometers or 11. Again, we would be very surprised to see something higher than 16 or something like this. Does that roughly answer the question? Okay.
Okay, gentleman at the front here. Sorry, Nick.
Last question, single question. Well, I can project my voice. You turned the last question into 2 questions. May I please ask 2? One is, how far away are these objects? And secondly, what are the signals that you actually receive? Presumably not visible light, but something else is arriving.
Just repeat the question, Andreas.
Yeah, so how far are these objects away? And what are the actual signals that we receive? How far they are away, again, since I'm not an astrophysicist, this answer will not be very concrete, but we have some objects in our galaxy, right? So these are the closest ones, but some beyond our galaxy, in other galaxies. We know about 3,000 neutron stars, so this might also be interesting. 2,800 or something like this. And the signals we receive, well, the most spectacular one I mentioned at the end, the gravitational wave, that's a new thing, right? Of these mergers, of these binary systems. There are also searches of gravitational waves from isolated stars, just by them being asymmetric and rotating. They might emit gravitational waves as well. But the more traditional ones are electromagnetic waves, not in the visible spectrum, but X-ray radio signals. Well, the picture to have in mind is, I didn't really explain this, but the typical signal of a neutron star that was first discovered in the 60s is that of a pulsar. And by pulsar, I mean an object that is rotating, so think of a rotational axis, how do I want to do this? So rotational axis like this, and a magnetic field axis that's a bit tilted. And the radiation goes out preferably along the magnetic field axis. But what this object now does is this, right? So my finger is the direction of the radiation we observe, some radio signal, and the rotation axis is in the middle. So if the Earth now happens to be here, what we see is a flashing signal, like a lighthouse, right? So that's how we can observe, for example, that's why we can, for example, measure the rotation frequency quite accurately, right? Much better than many of the other things. So that's one of the signals, or the typical signal of a pulsar, which is a neutron star.
Right, thank you for mentioning the pulsar. So what we knew as a pulsar, as a strange new object, then is what you're now calling a neutron star.
Yes.
Thank you.
Might even be more exotic as a neutron star. Remember, I talked about this quark matter, right? So a neutron star is, in some sense, a conservative name, because there might be more exotic matter inside.
Tony.
Yes, thank you. Andreas, why does stuff spin? Whether it's a galaxy, which is huge, or a subatomic particle, which is so small I don't know how you measure it, they all spin. But there's other things that don't spin. So why does stuff spin?
Actually, it's also two questions because the microscopic particles you mentioned, they spin for, I would say, a slightly different reason. It's got to do with quantum mechanics. So there's something called spin in quantum mechanics, which is different from macroscopic objects just rotating, right? So in the context of neutron stars, the general answer is it depends on the history of this object, right? I'm not sure if I have a good answer to your question, why does stuff spin? But in the case of a neutron star, the progenitor star has some spin, and it explodes and contracts to a neutron star, and then the spin can get faster, right? That's a bit like an ice dancer pushing the arms to the body, and then you get faster, right? So angular momentum is conserved. That's the technical way of saying it. Right, then you can ask, why did the progenitor star spin? Right, so this depends on the evolution. You have to start from some initial state, how the universe was made, how this stuff evolved. But I don't think I have a...
So why does it spin? You've been talking about how it spins. Why? Why does it need to spin? Why can't it just be a lump?
Stay still.
Maybe one answer is that things aren't always symmetric in nature, right? So a lump that just stays there is more symmetric than a spinning object. A spinning object has an axis, right? So you break some symmetry. That's a general concept that we see all over the place. Maybe that's one answer to your question. No? It's the best I can give.
Leave the man alone, Tony. Gentleman right at the back there. I'm really not picking these on purpose, Nick. It's just
Might have to stop for rationing.
Who was it?
Do the gluons that hold the quarks together inside a nucleon also hold the nucleons together?
The answer is yes, but in a less direct way, yes. So the nucleons, the force between nucleons also comes from the strong interaction from QCD, that's the theory behind it. And in that theory, the only transmitter of the force are the gluons. Right? So in an indirect way, yes. So this nuclear force comes from the gluon in an indirect way. I mean, if you're doing nuclear physics, then often you use effective descriptions. You don't work with the gluons themselves. You work with an exchange of what's called mesons or pions or something like this. But fundamentally, what's behind that is gluons. So the answer is yes.
Gentleman at the back, we'll give Nick a break, because the gentleman at the back also got his hand up.
You talk about gravitational waves, which in my small brain I can only picture as a ripple in space-time. How do they manifest themselves on Earth? What will we notice?
Well, it's basically, let's forget about space-time, let's make it simpler and say space is oscillating. So it's basically space contracting and expanding. That's already, also for me, not so easy to imagine, because it's space itself, right? It's not some object that expands in space, it's space itself. And this you measure by, I didn't explain the principle behind this detection, but I showed the picture. This you measure by constructing these two long arms in an L shape. These are about 4 kilometers long. And what you basically measure, so there's a signal coming from here, very far away, gravitational waves traveling to the Earth, and very weakly contracting and expanding space, and thus also contracting and expanding this whole arm. So roughly speaking, you measure a change in the length of that arm that is oscillating. Right? And this is usually done, so measuring tiny changes, and to explain how tiny this is, it's, I hope I quote this number correctly, it's some fraction of the size of a proton. I think it's 1,000th of the size of the proton that this arm changes in length. And that's why I said there's a lot of technology, and I'm not an expert at all in this kind of technology they use. I mean, the keyword is interference. You send lasers along these arms and let them then interfere, and from the interference you conclude that there is a gravitational wave going through.
Now there was a hand up at the front earlier, this lady, and I will use Andreas' mic to save Nick's legs. There we go.
In an object so dense, how is the magnetic field generated?
That's a very good question. The short answer is we don't know. It's a matter of current research. Why are these magnetic fields so large in the star? I mean, one partial answer again comes from the progenitor star. It's some magnetic field that's somehow enhanced in the process of the supernova. But really, we don't know. Excuse me. Yep, that's the answer.
Okay, I'll find out.
Honest.
I'll come
Gentleman
back.
in the middle there in the blue pullover. Dark blue pullover. Well, light blue. We'll get him going.
Andreas, does every supernova result in one or more neutron stars? And are neutron stars always the result of a supernova?
Can be black holes as well. Depends on the mass of the star you start with.
Short answer there. So, pass it straight back to the gentleman in the light blue.
Gravity, as you've explained it, seems extremely weak. Tiny things. I don't find myself being crushed into a neutron star. How is gravity able to link this together?
Because it's a lot of stuff concentrated in a small region. It's the compactness that makes it. You're absolutely right that gravity is a weak force compared to the other ones. Right. It's in some sense, in a strict sense, it's the weakest of these four forces. Right. So one way of saying this is take two electrons, And you can basically forget about their attraction due to gravity. It's only the electromagnetic charge that matters. But if you have a lot of mass, and notice also that the masses, the effect doesn't cancel each other, right? In electromagnetic charge, you have positive and negative, they can cancel each other, right? But in mass, when you lump mass together in a small region, then gravity gets big, right? And this becomes very extreme in objects like neutron stars, even more so in black holes. There the mass is even more concentrated in an even tinier region. So in terms of gravity, that's even more extreme. So it's really the compactness, putting all that matter in a small place that makes gravity so strong for these kinds of objects.
Gentleman in tartan collar down there. Yep.
You showed a graph that had hydrogen and helium at the surface. Could you give a sense of what's going on there? And do you get any nuclear fusion?
I don't know much about the surface, to be honest. Yes, you do get nuclear processes, like fusion as well. One concrete mechanism is accretion from other companion stars. So this does happen. So these nuclear processes go, actually they occur in what I call the crust here even, right? So this is nuclear reactions play a big role here. What exactly happens at the surface or also the atmosphere, it's also called atmosphere in this case. I'm just not an expert at all in this, so I can't say too much about this. I think we are not completely sure about the composition. We roughly know what's going on. I mean, as you say, it says hydrogen, helium. So we certainly know more about that than about the core. But I think there are even also some open question what exactly this surface is. I mean, for me as a particle physicist, it's not that interesting. But obviously, for modeling or interpreting data from the star, because it comes from the surface eventually, right? That's certainly important. So we have to understand that in order to interpret the results or the signals that we get from the star.
There was another hand up near that gentleman, just over. Yeah. Oh yes, the gentleman in the green shirt. Yeah.
Hi. You mentioned that there were 6 flavours of quarks. We've only really talked about 2 of them. Where are you expecting to find the other 4, and why aren't they in normal protons and neutrons?
Okay, so just to mention this for everybody, so we are on the most fundamental level all made of up and down quarks. So that's the 2 flavors, right? So the neutrons and protons are all made of 2 quarks only. We know from experiments in accelerators that there are 6, so we've seen 6. And the reason why they're usually not that important, also here, I mean, I mentioned the 3rd one, by the way. That was my remark, very short, about strangeness, strange quark matter. So there's a 3rd one. The reason why they, even in this extreme matter, do not appear, the heavier ones, is that they are very massive.
Inside?
No, they have a mass.
Oh, right.
Each quark flavor has a mass. And the up and down are the lightest ones. The strange is a bit heavier. And the 3 other ones are even heavier. Right? And you always need, so energy is the same as mass, as Einstein told us. So we need a huge amount of energy to create these heavy flavors. Right? And in experiments we can do this. But here, for this kind of matter, 3 is the maximum number of flavors we have to worry about.
Gentleman over here on the
Reclining at leisure on the intellectual seats.
Hiya. You mentioned superconducting and superfluid. I've got a rough idea of superconducting. What's a superfluid?
Theoretically, it's very similar. Depends a bit on what your idea of a superconductor is. So if you're talking about the fundamental or the microscopic mechanism for superconductivity, which is Cooper pairing, not sure if this rings a bell, that's probably more for the experts. So Cooper pairing is the same that happens in the superfluid also. The difference is that the particles that form these pairs do not carry electric charge while they do so in a superconductor. More more practically speaking, while a superconductor can have a current without resistance, a superfluid can flow without friction. That's probably better. I should have started with that one before I went into Cooper pairing. So that's the simple answer. But still interesting to note that the microscopic mechanism is very similar. So from a theoretical point of view, they are closely connected.
Can I ask a question? Yeah, you again. Hear the question.
Do you think that this research could have any impact on ongoing technology and computers and stuff like that?
He's asking if it's any practical use.
I could also make it short and say no. I mean, it's the honest answer that this research is driven by fundamental questions, right? So we're interested in the laws of nature, right? If you wish, it's even a cultural motivation to understand nature. As I just talked to some people in the audience during the break, obviously there are many examples in the history of science where these questions much later, led to new technological developments, right? But that's so hard to foresee that my honest answer is I don't know what this really is good for in the future, right? So I'm driven by fundamental questions there. But it's certainly not excluded that this has some applications in 50 years from now. But I have no idea which ones. So.
I think with that, we have to draw the questions section to a close. Thank you for all the questions. I think Andreas deserves another round of applause for trying to answer them.